One of the most intriguing aspects of cosmic inflation is how it helps solve several long-standing puzzles about our universe's earliest moments, questions that standard Big Bang theory alone couldn't fully explain. Before scientists introduced the idea of inflation, they struggled to understand why the universe looked so uniform and smooth on large scales, and yet, at the same time, contained tiny irregularities that would later grow into galaxies, stars, and planets. The theory of cosmic inflation offers an elegant explanation for both of these surprising features. To appreciate why inflation is so important, we need to consider what astronomers observe when they look at the cosmic microwave background, CMB. This ancient light is a kind of fossil radiation left over from about 380,000 years after the Big Bang, and it offers an incredibly detailed snapshot of the universe at that time. What makes the CMB remarkable is how exquisitely uniform its temperature is across all directions in the sky. The differences are incredibly small, only about 1 part in 100,000. This uniformity presents a challenge. If the universe expanded at a constant rate from the Big Bang, there wouldn't have been enough time for all these widely separated regions to communicate or exchange energy and information, yet they exhibit almost identical temperatures and densities. This puzzle is often called the horizon problem. The term horizon here refers to the maximum distance over which objects could have influenced each other since the beginning of the universe. Under normal expansion rates, regions of the universe on opposite sides of the sky simply couldn't have exchanged signals or particles because light wouldn't have had enough time to travel between them. Yet the CMB suggests these regions did reach the same temperature and conditions, which means something unusual must have happened early on. Cosmic inflation provides a compelling solution. It posits that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid expansion, growing exponentially larger at speeds so fast they outpaced even light. It's important to clarify this point because it might sound like a violation of Einstein's theory of relativity. However, cosmic inflation doesn't violate relativity because it's not about objects moving through space faster than light. Instead, it's space itself that is expanding, carrying galaxies, and everything else embedded in it, along for the ride. General relativity permits space to expand faster than light under the right conditions. So how fast did this expansion happen? During inflation, the universe could have expanded by a factor of at least 10^26 in less than a trillionth of a trillionth of a trillionth of a second. To visualize this staggering number, imagine something the size of a proton suddenly blowing up to something much larger than a grapefruit in an unimaginably brief moment. This explosive growth smoothed out any bumps or wrinkles, creating the remarkably uniform cosmos we observe. But while inflation smoothed things out, it didn't eliminate all irregularities. Tiny quantum fluctuations, minute variations rooted in the fundamental laws of quantum mechanics, were stretched from minuscule scales to cosmological sizes by inflation. These fluctuations acted as the seeds for the formation of all the structure we see today: galaxies, clusters of galaxies, and vast cosmic webs. Without inflation, these primordial irregularities would be difficult to explain, as traditional Big Bang models would have left the universe either too lumpy or too smooth. Another significant mystery that inflation helps illuminate is the flatness problem. Measurements indicate that the universe's overall geometry is very close to flat, meaning that the rules of Euclidean geometry largely apply on cosmic scales. Parallel lines stay parallel, and the angles of triangles add up to 180 degrees. This flatness is a delicate state, and without some mechanism to enforce it, the universe would quickly drift toward being either positively curved like a sphere or negatively curved like a saddle. Inflation naturally drives the universe's shape toward flatness by stretching space, to such an extent that any initial curvature would have been flattened out. Much like inflating a balloon makes its surface appear flatter as it grows. The final major puzzle that inflation addresses is the monopole problem. According to certain particle physics theories, the early universe should have produced exotic, massive particles called magnetic monopoles, hypothetical particles with just a single magnetic pole instead of the familiar north and south pair. Though these particles have never been detected, the models suggested that if they did exist, they would have been produced in vast quantities, enough to dominate the universe's mass. Since we don't observe magnetic monopoles flooding the cosmos, their absence was a troubling mystery. Inflation solves this by diluting the concentration of any monopoles or other heavy relics, spreading them so thin across space that the likelihood of encountering them today is extraordinarily low. Beyond solving these foundational problems, the idea of inflation has enjoyed strong support through precise measurements of the CMB, including data from NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck satellite. These measurements revealed the pattern of temperature fluctuations with great sensitivity, matching predictions made by inflationary models in exquisite detail. This agreement has been a major reason why inflation is now the leading theory for the universe's earliest moments. While inflation explains much, questions remain about the exact cause of this rapid expansion. The leading idea involves a mysterious energy field called the inflaton field. Just as other known fields, like the electromagnetic field, affect forces and particles, the inflaton field would have driven the expansion by its own peculiar properties. As the inflaton field lost energy, inflation slowed down and ended, leading to a phase called reheating, in which the energy stored in the inflaton field converted into ordinary particles, giving rise to the hot, dense universe that evolved according to the Big Bang scenario we know. Understanding the inflaton field is a major focus of ongoing research, bridging insights from cosmology, quantum physics, and particle physics. The quest continues to identify the precise nature of this field, its connection with other fundamental forces, and how it fits into a unified theory of physics. Despite these mysteries, the basic principle that the universe underwent a blisteringly fast expansion remains a cornerstone of modern cosmology. This glimpse into cosmic inflation illustrates how a brief, nearly instantaneous event can have layered consequences that echo through billions of years of cosmic history. By stretching the fabric of space itself, inflation set the initial conditions for a universe both remarkably uniform and richly structured, a stage on which galaxies, stars, planets, and life itself would eventually emerge. While the details of how and why inflation started continue to unfold, the theory represents one of the most successful efforts to understand the universe's earliest chapter. It teaches us that the story of our cosmos includes moments so extreme and fast that they challenge our everyday intuition, inviting us to explore the fundamental laws that govern everything we see and even what lies beyond. With these insights in mind, it becomes clear that cosmic inflation is not just a distant event confined to the universe's infancy, but a profound key to unlocking the grand narrative of space, time, and matter. It reminds us that to grasp where we come from, we must sometimes look at the very smallest scales of energy and the very largest scales of space expansion, both intertwined in the remarkable phenomenon that shaped everything we observe today. To better understand the profound implications of cosmic inflation, it helps to explore how this theory meshes with the broader framework of physics and how it fits into our quest to comprehend the earliest moments of the universe. Inflation is deeply tied to the laws of quantum mechanics and general relativity, two pillars of modern physics that traditionally describe very different scales. Quantum mechanics governs the minuscule world of particles and atoms, while general relativity governs the cosmic scale of stars, galaxies, and the structure of spacetime itself. Cosmic inflation sits at the crossroads where these two realms meet. At the heart of this connection lies the idea that during inflation, quantum fluctuations, the tiny, random jittering of energy that occurs even in empty space, became the seeds of all large-scale structure in the universe. To imagine this, picture a small region of space smaller than an atom with energy fluctuating due to quantum effects. Inflation stretched this tiny region exponentially, magnifying these energy differences to astronomical sizes. This process turned imperceptible quantum ripples into gravitational irregularities, which over billions of years grew into the galaxies and clusters of galaxies we observe today. The mathematics behind this phenomenon involves quantum field theory in curved spacetime, an advanced framework that combines quantum mechanics and general relativity. While the details are quite complex, the result provides a natural explanation for why the density variations in the early universe were nearly, but not perfectly uniform. Exactly what scientists measure today in the cosmic microwave background radiation. These faint fluctuations form a fingerprint of the inflationary period, allowing physicists to test their theories against observations with remarkable precision. Another key concept in understanding inflation concerns the role of energy and the nature of space itself. In everyday terms, energy can push or pull on matter, but in the context of inflation, it's the energy inherent in space that drives expansion. This energy is associated with a property known as vacuum energy or the energy of empty space. During inflation, the universe was dominated by this energy density, which had the unusual effect of causing space to expand faster and faster. You might wonder, if space expands so rapidly during inflation, what happens once this phase ends? After inflation ends, the universe enters a phase called reheating, during which the enormous energy stored in the inflating field converts into the particles and radiation that make up the familiar hot, dense early universe. From this point, the universe expands more slowly, governed largely by gravity acting on matter and radiation. This transition sets the stage for all the processes that shape the cosmos, including the formation of atoms, stars, and eventually planets. Interestingly, the concept of vacuum energy during inflation connects to a mysterious phenomenon observed in our universe today known as dark energy. While the two are not identical, both involve energy intrinsic to space that affects its expansion. Dark energy is thought to be responsible for the current accelerated expansion of the universe billions of years after inflation occurred. This link reveals a remarkable symmetry in cosmic evolution. Brief but enormous expansion in the past and slow, ongoing expansion in the present, both seemingly driven by the properties of space itself. Inflation also raises profound philosophical and scientific questions about the initial conditions of the universe. For instance, what triggered the inflated field to begin its rapid expansion? Why did it stop, allowing for the universe to cool and matter to coalesce into more complex structures? Scientists consider these questions fundamental because they address the very nature of physical laws and the origins of the cosmos. One leading approach scientists pursue involves refining the microscopic models of particle physics that might describe the inflated field. Some theories propose connections between inflation and the unification of fundamental forces, suggesting that inflation might offer a window into physics beyond what we can currently probe with experiments like particle accelerators. However, these theoretical frameworks remain speculative until experimental confirmation becomes possible. Despite these open questions, the inflationary model has passed stringent tests and remains favored because it consistently matches observational data better than competing theories. For example, it explains why the universe is so large and so uniform, while naturally allowing for the small irregularities that set the stage for all complex cosmic structures. Without inflation, the universe would be harder to explain in terms of its origin and subsequent evolution. In addition to observational data from the cosmic microwave background, scientists seek further evidence for inflation through the search for primordial gravitational waves. These ripples in spacetime, if detected, would provide a smoking gun signal of inflation. Generated by the same quantum fluctuations that seeded density variations, gravitational waves would stretch and squeeze spacetime itself. Experiments such as the Laser Interferometer Gravitational Wave Observatory, LIGO, and next-generation cosmic microwave background observatories are actively searching for these subtle signals. The detection of primordial gravitational waves would not only bolster inflationary theory, but also provide unprecedented access to information about the universe at energies trillions of times greater than can be achieved on Earth. Such a discovery would mark a turning point in cosmology, connecting theories of the very early universe with fundamental physics and potentially pointing toward a deeper theory of everything. From a broader perspective, cosmic inflation invites us to reconsider the nature of time and space. It implies that what we call the beginning of the universe may not be a singular moment, but part of a more complicated process in which the universe undergoes phases of rapid growth and transformation. Some models even explore the idea that inflation could be eternal, occurring repeatedly in different regions of space, giving rise to countless bubble universes, each with their own properties. While this idea, known as eternal inflation, pushes beyond direct empirical testing at present, it demonstrates how inflationary cosmology interfaces with fundamental questions about the nature of reality itself. Yet even without embracing these speculative ideas, the theory of cosmic inflation has profoundly reshaped our understanding of the universe's first fractions of a second. It takes us deep into a realm where space and time behave in ways entirely unfamiliar from everyday experience, governed by the extraordinary yet well-defined laws of physics. The significance of inflation extends beyond mere technical details. It reflects humanity's relentless curiosity and ability to piece together a coherent story of origins from the faintest signals and the most subtle clues. It reminds us that large-scale phenomena like galaxies and clusters trace back not to grand, visible forces, but to quantum jitters magnified by cosmic forces billions of years ago. The influence of cosmic inflation continues to permeate modern cosmology. Researchers use it as a foundation to refine our understanding of dark matter, dark energy, and the ultimate fate of the universe. It also informs astrophysical models of how the earliest stars and galaxies formed after the universe cooled enough for matter to clump together. In this way, inflation provides both a beginning and an ongoing framework for interpreting a vast array of cosmic phenomena. In practice, the study of cosmic inflation exemplifies the interplay between theory, observation, and experiment that drives scientific progress. Observations like the detailed measurements of the cosmic microwave background offer data that theories must explain, while theoretical advances propose new phenomena to look for. Experiments then strive to detect these signals, pushing technology and ingenuity forward. Looking ahead, upcoming space missions and ground-based observatories aim to sharpen our view of the universe's initial conditions. Projects like the Simons Observatory, the CMBS-4 experiment, and future space telescopes seek to refine measurements of the cosmic microwave background with unprecedented sensitivity. The hope is to uncover subtler features predicted by inflationary models, clarifying the dynamics of inflation and potentially revealing new physics. Additionally, developments in particle physics, such as experiments at the Large Hadron Collider and proposed next-generation colliders, may shed light on the nature of the inflated field by discovering new particles or forces that tie into inflationary scenarios. This cross-disciplinary approach illustrates how cosmic inflation connects the very small with the very large, revealing unity in the physical laws that shape the cosmos. In conclusion, cosmic inflation stands as one of the most remarkable and well-supported ideas in modern cosmology. It explains how the universe transformed from an unimaginably tiny, hot, and dense state into a vast expanse with the intricate structures we observe today. It bridges theoretical physics and observational astronomy, embodying the exquisite dance of the cosmos governed by fundamental laws. As research continues and technology advances, the story of cosmic inflation will undoubtedly grow richer, deepening our understanding of where we come from and how the universe became the remarkable place it is, and perhaps guiding us toward new discoveries that transcend even our current imagination. To delve deeper into cosmic inflation, it's essential to understand how the theory connects to the fundamental forces and particles that govern the universe. Inflation not only describes the rapid expansion of space, but also links closely with the behavior of these forces at extraordinarily high energies. In the earliest moments of the universe, just after inflation ended, conditions were so extreme that the familiar distinction between forces, gravity, electromagnetism, and the strong and weak nuclear forces, may have been blurred or unified. Studying inflation, therefore, offers a rare glimpse into physics at energy scales far beyond what can be recreated in laboratories on Earth. One reason this connection is important lies in the quest for a theory of everything, an all-encompassing framework that seamlessly incorporates quantum mechanics with general relativity and unites the fundamental forces into a single description. Inflationary cosmology invites physicists to consider how such unification might have influenced the earliest universe's behavior. For instance, certain inflation models derive their dynamics from fields related to grand unified theories, GUTS, speculative frameworks where the electromagnetic, weak, and strong nuclear forces merge at extremely high energies. The decay or phase transitions of these fields during and after inflation could have released tremendous energy, shaping the evolution of the cosmos. The mathematics underlying inflation is rich and sophisticated. It often involves scalar fields, which assign a numerical value to every point in space and time. The inflaton field, responsible for inflation, is understood as a scalar field with a specific potential energy shape. This potential determines how the field evolves and drives expansion. Different inflationary models propose varied shapes for this potential, and the precise form influences observable consequences, such as the pattern and scale dependence of primordial fluctuations imprinted on the cosmic microwave background. Scientists test these models by comparing predictions to data from observational missions like Planck and WMAP, gradually narrowing down the possibilities. Another critical concept linked to inflation is the idea of symmetry breaking. In the high-energy environment of the early universe, many physical symmetries may have been intact, meaning that the laws of physics exhibited uniform behavior without preference for certain directions or states. As the universe cooled and inflation ended, these symmetries could have broken, similar to how water freezes into ice with an ordered crystalline structure. This breaking gave rise to the distinct forces and particles we observe today. Certain inflation models incorporate this process of symmetry breaking, tying cosmic evolution to the fundamental characteristics of particles and forces. To illustrate the significance of inflation's effects, consider the cosmic microwave background once more. The minute temperature fluctuations measured in this radiation are not random. They follow precise statistical patterns expected from quantum fluctuations stretched during inflation. These tiny variations extend across various angular scales, reflecting the physics of the inflaton field and the conditions at the very origin of the universe. The fact that these patterns match inflationary predictions distinguishes inflation from alternative early universe scenarios, reinforcing its status as the leading explanation for the universe's initial moments. Looking beyond the cosmic microwave background, inflation also predicts the existence of primordial gravitational waves, ripples in spacetime itself that originated during inflation. These gravitational waves would leave a distinct imprint known as B-mode polarization in the polarization pattern of the CMB radiation. Detecting this signal has become a major goal of observational cosmology, as it would provide direct evidence of inflationary dynamics and the high-energy processes involved. Various experiments, such as BICEP/Keck array and upcoming missions like LIGHTBIRD, are designed specifically to probe these subtle signatures. The stakes involved in detecting primordial gravitational waves are high because their properties reveal details about the energy scale of inflation. A positive detection would allow scientists to infer the precise energy at which inflation occurred, potentially exposing physics at energy levels 1 trillion times greater than those probed in particle accelerators. This would open a portal into territories beyond the standard model of particle physics, shedding light on the earliest epochs when space and time were shaped. The concept of reheating introduces another vital phase after inflation. Once inflation ends, the energy stored in the inflatoned field must transform into the diverse particles and radiation that populate the universe. This process, called reheating, bridges the inflationary epoch with the hot Big Bang conditions more familiar to cosmologists. During reheating, the universe heats up, setting the stage for nucleosynthesis, the formation of atomic nuclei, and later, the creation of atoms, stars, and galaxies. Reheating is not a trivial transition. Because details of how the inflatoned field decays remain uncertain, this stage is an active research area. Different models propose various decay channels and rates, which affect the evolution of the universe's temperature, the abundance of particles, and even subsequent phenomena like the generation of matter-antimatter asymmetry. Understanding reheating sheds light on how a nearly empty, rapidly expanding universe transformed into a hot, dense, and complex one. This transformation connects to another profound question. Why does the universe contain more matter than antimatter? When matter and antimatter meet, they annihilate, so the universe starting with equal amounts should have ended up devoid of matter. Yet we see a universe dominated by matter, allowing galaxies, stars, and life to exist. While cosmic inflation itself does not directly explain this asymmetry, the reheating era possibly provides conditions conducive to processes that generate matter exceeding antimatter. Thus, studying inflation and reheating ties into broader inquiries into the universe's composition and evolution. Importantly, inflation's implications extend far beyond the nature of the early universe. They shape how we interpret the cosmos on the largest scales. The theory predicts a near-scale invariant spectrum of primordial fluctuations, meaning the fluctuations have similar strength across a broad range of scales. This prediction aligns closely with observations, suggesting that the same physical laws and processes during inflation set a universal template for structure formation. From clusters of galaxies down to smaller galactic structures, this template still governs how matter clumps and evolves. As technology and observational techniques advance, scientists continue to refine measurements of cosmic parameters associated with inflation. For example, the spectral index describes how fluctuation strengths change with scale, and current data suggest it slightly deviates from perfect invariance, a detail lending insight into the inflationary potential. The amplitude of fluctuations, their symmetry, and other statistical properties provide stringent constraints on inflationary models. These constraints eliminate entire classes of models and push theory toward consistency with empirical data. The ongoing interplay between observation and theory exemplifies the scientific method at its best. Predictions from inflationary cosmology lead to concrete data to be sought, and in turn, data guide refinement and sometimes rethinking of theoretical frameworks. This iterative process advances our understanding steadily, even as it acknowledges the limits of current knowledge. Moreover, cosmic inflation raises profound questions about the nature of reality itself. The rapid stretching of space not only explains conditions within our observable universe, but also suggests that beyond what we can see, inflation may have generated regions with vastly different properties or even different physical constants. This idea opens the door to the concept of a multiverse, numerous pocket universes, with varying characteristics created by inflation's relentless expansion. While direct evidence for such a multiverse remains elusive and speculative, the possibility stimulates deep reflection on the limits of scientific inquiry and the scope of cosmology. At the interface of physics and philosophy, inflation challenges our understanding of time and causality. If inflation smoothed and expanded space so dramatically, then the notion of a simple, singular beginning becomes more complex. The initial singularity of the classical Big Bang may give way to a scenario where space emerges smoothly from some quantum state or previous phase. Some approaches explore quantum cosmology, seeking to describe how a universe could spontaneously arise from nothing in a mathematically consistent way, with inflation possibly serving as the mechanism that launches cosmic expansion thereafter. This perspective invites reassessment of concepts like cause and effect on cosmic scales. If the classical Big Bang is not the absolute beginning, but rather a transition, then questions about what came before, or what caused that transition enter domains currently addressed by theoretical models awaiting future empirical input. Despite such unresolved issues, cosmic inflation remains an extraordinary triumph of human ingenuity. It ties together diverse physical ideas, from quantum fluctuations to large-scale geometry, into a coherent explanation that matches remarkably well with cosmological observations. Its success underscores the power of combining theoretical insight with precise measurement to unravel nature's deepest mysteries. The development of inflationary theory also highlights the importance of creativity and openness in science. Before inflation was proposed, many cosmologists accepted the Big Bang on its own terms, assuming the universe's initial conditions were given and unexplained. The introduction of inflation revolutionized this view by suggesting a physical process that naturally generates those initial conditions, rather than taking them as arbitrary or special. Looking to the future, researchers aim to probe further into the inflationary era through a variety of initiatives. Next-generation cosmic microwave background experiments will increase sensitivity to primordial gravitational waves and refine measurements of temperature and polarization fluctuations. Large-scale structure surveys mapping millions of galaxies will test inflation's predictions about the distribution of matter. Complementary approaches, like laboratory experiments searching for hypothetical particles associated with inflation, will help close the gap between cosmology and particle physics. A promising frontier lies in exploring how inflation fits into the broader context of cosmic evolution, including its relationship to dark matter and dark energy. Both dark matter and dark energy account for roughly 95% of the universe's content, yet their nature remains largely unknown. Understanding inflation better may offer clues about these mysterious components by clarifying the underlying physics that governs the universe's large-scale behavior. There is also growing interest in connecting inflation to string theory and other frameworks attempting to unify all forces of nature. These theories predict rich landscapes of possible states and fields, some of which might correspond to inflationary scenarios. While much speculative at this stage, the dialogue between string theory and inflationary cosmology exemplifies the dynamic, multidisciplinary nature of modern physics. In practical terms, understanding cosmic inflation enriches how we perceive our place in the universe. It demonstrates that the cosmos's vast and complex structure stems from subtle origins, minute quantum ripples stretched by the dynamics of the inflaton. It reinforces the idea that the large-scale uniformity and local complexity coexist because of a common physical reason embedded in the universe's earliest moments. From a scientific perspective, cosmic inflation marks a watershed moment, revealing that the universe's birth was neither a static event nor a brute initial condition, but a dynamic process subject to laws yet to be fully unraveled. It challenges us to keep asking questions, to refine our understanding of the cosmos's beginnings, and to pursue empirical evidence that sheds light on some of the most profound mysteries known. Amid the grand narrative of cosmology, inflation holds a central place, knitting together the small and large, the quantum and cosmic, into a compelling vision of why the universe looks the way it does, and continues to evolve toward unknown futures. As we continue to explore this frontier, cosmic inflation invites us into a deeper dialogue with nature, inspiring curiosity and study that will shape the years, perhaps centuries, of scientific inquiry to come. To appreciate just how transformative cosmic inflation is, it's helpful to consider how it reshaped the timeline of the universe itself. Before inflation was introduced, the traditional Big Bang framework portrayed the universe as expanding steadily from an incredibly hot and dense initial state, but left crucial questions about those earliest instants unanswered. Inflation inserts a new phase, a brief epoch dominated by rapid expansion, occurring within a fraction of a second after what we call the Big Bang. This tiny window fundamentally altered the conditions under which the universe began to evolve into its present form. One impressive outcome of inflation is how it created a universe large and uniform enough to encompass the diversity of cosmic structures we observe, while also embedding subtle fluctuations that eventually led to the galaxies and clusters we see today. This dual accomplishment resolves the balance between order and complexity, which had previously been a difficult puzzle. Without such a rapid expansion smoothing out irregularities and then stretching quantum fluctuations, the universe might look vastly different, either too chaotic or too homogeneous for stars, planets, and ultimately, life to form. Beyond restructuring the universe's early moments, inflation also refined our understanding of cosmic parameters, fundamental numbers that describe the universe's composition, expansion rate, curvature, and density. For example, the density parameter, often denoted by omega, measures the amount of matter and energy relative to the critical density required for a flat universe. Inflation predicts omega should be extremely close to 1, implying a flat universe, which observation confirms with remarkable precision. This sharp alignment between theory and measurement is a testament to inflation's predictive power. Another key parameter influenced by inflation is the so-called spectral index, which describes the scale dependence of the primordial fluctuations, how the strength of temperature variations in the CMB changes with the scale observed. Inflation predicts a value slightly less than 1, indicating that smaller fluctuations are marginally stronger on larger scales compared to smaller ones. Measurements from satellites like Planck have found spectral indices matching this prediction, reinforcing confidence in inflation's foundational role. To illustrate inflation's impact on cosmic evolution, imagine the contrast between the universe's size before and after this explosive growth. Prior to inflation, the entire observable universe could fit inside a volume smaller than a single atom, yet it already contained the seeds of all future structures. Inflation catapulted this minuscule region to macroscopic dimensions in an instant, setting up the cosmic landscape from which galaxies and clusters would later emerge. This dramatic stretching is challenging to visualize, but essential for grasping why the universe today is so enormous and yet displays underlying uniformity. It's worth pausing to clarify how inflation relates to the idea of the Big Bang itself. Inflation does not replace the Big Bang, but complements it by providing details about the universe's initial expansion and conditions. The Big Bang remains the term for the hot, dense state from which the universe began expanding and cooling in the conventional sense. Inflation, occurring immediately before and leading into that phase, explains how the universe reached the conditions necessary for the Big Bang model's subsequent predictions, such as nucleosynthesis, the formation of light elements, and cosmic background radiation, to hold true. The process that ends inflation is equally important. While inflation causes space to expand exponentially, this phase cannot continue indefinitely. Eventually, the inflatened field that drives inflation loses energy and rolls down its potential energy landscape, ending the rapid expansion. This transition is akin to a ball rolling to the bottom of a hill after climbing to the peak. The energy released during this descent converts into a hot soup of particles and radiation during reheating, beginning the familiar hot Big Bang phase. Interestingly, the end of inflation marks the beginning of a universe that behaves more in line with everyday physics, expanding more slowly under the influence of gravity acting on matter and radiation. This shift from rapid, accelerated expansion to a more gradual cooling and expansion sets the stage for the formation of atomic nuclei roughly 3 minutes later, as the universe's temperature dropped enough for nuclear fusion to occur. These nuclei would later form atoms, which combine to create stars, galaxies, and planets over billions of years. The concept of reheating, bridging the inflationary period and the hot Big Bang, is not just a theoretical curiosity, but a crucial piece in understanding how particles and forces interact at extreme energies. It explains how the universe became filled with the familiar particles in the right proportions to form everything we know. Different models of reheating explore how efficiently and quickly the inflatened field decays into matter and radiation, influencing the thermal history and subsequent evolution of the universe. This process also has implications for the matter-antimatter asymmetry observed today. Although inflation sets the stage for a hot, dense universe, the question of why there's more matter than antimatter remains pressing. Some theories propose that mechanisms during or shortly after reheating could generate this asymmetry through processes violating fundamental symmetries in particle physics. Exploring this connection is an ongoing pursuit linking cosmology with particle physics experiments. Because the energy scales involved in inflation are incredibly high, far beyond what current particle accelerators can reach, cosmologists rely heavily on indirect methods of investigation. Observations of the cosmic microwave background and large-scale structures serve as cosmic laboratories, preserving the subtle imprints left by inflationary processes. By measuring these patterns with increasing precision, scientists piece together the detailed physics that govern the early universe. One fascinating aspect of inflation is how it amplifies quantum mechanics from microscopic scales to cosmic ones. Quantum fluctuations in the inflatened field produce tiny variations in energy density that inflation then stretches across vast expanses of space. These variations are the progenitors of the galaxies and large-scale structures we observe. Thus, the tiny quantum noise characteristic of all physical fields during inflation plays a fundamental role in shaping the universe's macroscopic features. To understand these effects more concretely, researchers use powerful computer simulations to model how these primordial fluctuations evolve under gravity over billions of years. Starting from the initial conditions set by inflation, such simulations recreate the formation of the cosmic web, the vast network of galaxies and clusters linked by filaments of dark matter. By comparing simulations to actual galaxy surveys, scientists test whether inflation's predictions hold up across cosmic scales. Crucially, inflation does not predict perfectly uniform fluctuations, but rather a particular statistical distribution that matches observations remarkably well. These fluctuations also exhibit a slight preference for Gaussian statistics, meaning essentially that the variations follow a bell-shaped curve, which is confirmed by data from the cosmic microwave background. Any significant deviations from Gaussianity would challenge inflationary models, making this an important area of study. While inflation provides many answers, it also raises new questions about the mismatch between quantum mechanics and gravity. Understanding how these two pillars unite in the inflationary epoch could illuminate quantum gravity, the theory that reconciles general relativity with the probabilistic nature of quantum mechanics. Approaches such as string theory and loop quantum gravity attempt to address these issues, with some proposing variations on inflation or alternative scenarios. One particularly intriguing avenue involves the possibility of eternal inflation, where inflation never completely ends but continues in some regions of space, spawning multiple bubble universes. This idea suggests that our observable universe is just one patch within a larger multiverse. Each bubble universe could have different physical properties or constants. While this notion pushes far into theoretical territory, it stems directly from the mechanisms underlying inflation. At a more practical level, scientists seek to validate inflation through experimental detection of primordial gravitational waves, ripples in spacetime predicted to arise from inflationary quantum fluctuations. Measuring these waves in the polarization patterns of the cosmic microwave background would provide direct evidence of inflation's high-energy physics. Projects like the BICEP series and planned space missions aim to detect these signals, pushing the limits of observational cosmology. If detected, primordial gravitational waves would also help estimate the energy scale at which inflation occurred, informing particle physics and offering clues about forces beyond the standard model. This connection illustrates how inflation acts as a bridge linking the universe's earliest moments to fundamental physics. Beyond gravitational waves, inflationary cosmology also interacts with the study of dark matter and dark energy, two mysterious components comprising most of the universe's mass energy. While inflation itself does not directly explain these phenomena, its mechanisms set the initial framework within which these components evolve. Understanding the full cosmological picture requires integrating inflationary physics with ongoing studies of dark matter's nature and dark energy's role in driving the universe's accelerated expansion today. Over time, refined data from cosmic microwave background experiments, galaxy surveys, gravitational wave observatories, and particle accelerators will further hone inflationary models, potentially uncovering new physics or revealing limitations of current theories. This dynamic process exemplifies how cosmology is an observational and theoretical frontier, advancing with improved experimental tools and mathematical insights. The enduring influence of cosmic inflation illustrates the profound impact of hypothesizing processes occurring within tiny fractions of a second after the universe's birth. It reveals how the interplay between quantum phenomena and cosmic-scale dynamics shapes the very fabric of reality. Inflation connects the primeval instant to the vast cosmic structures we inhabit, galaxies, stars, and ultimately planets and life itself. In sum, cosmic inflation remains a cornerstone of modern cosmology because it offers a coherent, testable framework for explaining the universe's earliest evolution, the distribution of matter and energy, and the large-scale structure we observe. By converting minute quantum ripples into the scaffolding of all cosmic structures, it exemplifies the power of fundamental physics to uncover hidden layers of reality. As science advances, Inflation continues to inspire efforts to deepen our understanding of the cosmos, pushing the boundaries of knowledge about where we come from and how the universe functions at its most fundamental level. Beyond its profound explanatory power, cosmic inflation also reshapes how scientists think about the fundamental nature of the universe's beginnings. Traditionally, the Big Bang was often pictured as a singular moment, a precise starting point where time and space came into existence. Inflation adds nuance to this picture by introducing a dynamic phase just after the universe's initial formation, suggesting that what we call the beginning might be more complex than a single instant. One key insight from inflationary theory is the idea that the universe's initial conditions could themselves be the result of earlier physical processes governed by quantum mechanics. In this view, the inflated field and the rapid expansion it triggered may be part of a cycle or a transition from a prior state that is not well understood yet. Some theoretical frameworks propose that the universe may have emerged from a quantum vacuum fluctuation or a pre-existing, eternal state. However, since these ideas push the limits of current physics, they remain areas of active research rather than established facts. Understanding where inflation itself begins touches on subtle issues in quantum cosmology, a field seeking to apply quantum principles to the universe as a whole. Here, the classical notion of time may break down and space might not have a clear boundary or edge. Instead, the universe might have a finite past without a conventional beginning, much like the surface of Earth has no edge, only curvature. Inflation, with its rapid expansion and smoothing effect, could then be seen as a bridge connecting a quantum origin with the large, classical cosmos we inhabit. This perspective also influences how physicists consider the multiverse hypothesis. Some inflation models suggest that inflation never ends uniformly everywhere but continues in patches, producing an array of distinct bubble universes, each potentially governed by different physical laws or constants. While this idea remains speculative and difficult to test directly, it arises naturally from the mechanics of inflationary expansion combined with quantum effects. The existence of such a multiverse would have profound implications for our understanding of fundamental physics and the uniqueness of our own universe. Moving from the conceptual to the empirical, one of the most promising routes to deepen our knowledge about inflation involves the search for subtle imprints left on the cosmic microwave background. While early missions like WMAP and Planck mapped temperature fluctuations with extraordinary detail, new experiments target the polarization patterns of the CMB, specifically looking for signals called B-mode polarization. This pattern would reflect the twisting effects of primordial gravitational waves generated during inflation's rapid expansion. Detecting B-mode polarization would be a groundbreaking confirmation of inflationary theory, directly connecting the physics of quantum fluctuations to observable phenomena on the largest scales. The challenge is considerable because these signals are incredibly faint and must be distinguished from foreground emissions like dust in our galaxy. Experiments such as the BICEP/Keck array and upcoming telescopes like the Simons Observatory and Light-Bird aim to overcome these obstacles by combining sensitive instruments with refined data analysis techniques. Beyond gravitational waves, advancing our understanding of inflation requires more precise measurements of galaxy distributions and large-scale structures. Galaxy surveys like the Dark Energy Spectroscopic Instrument DAISY and the Vera-C Rubin Observatory map the universe's structure across vast distances, allowing scientists to compare observed clustering patterns with inflationary predictions. Since inflation sets the initial density fluctuations, any discrepancies or new features discovered can refine or challenge existing models. Moreover, as large astronomical datasets grow, computational methods like machine learning and advanced simulations become critical tools. These approaches help analyze complex patterns in cosmic structures, linking them back to the primordial fluctuations seeded during inflation. Through this synergy of observation and computation, researchers aim to resolve finer details that could reveal the inflated field's nature or hint at new physics beyond current models. The particle physics side of inflation research continues to focus on identifying candidates for the inflated field and understanding how it fits into the broader framework of fundamental forces and particles. The inflaton is typically modeled as a scalar field, unlike the vector fields describing electromagnetism, whose potential energy drives expansion. However, determining which particle or field in nature actually corresponds to the inflaton remains elusive. Certain theoretical approaches suggest that the inflaton might be related to particles predicted by supersymmetry or linked to hidden sectors beyond the standard model. Others explore the possibility that the inflaton field is an effective description of more complex dynamics at high energy scales, such as those arising in string theory or extra-dimensional models. Current and future particle collider experiments aim to discover new particles or phenomena that could provide clues about this epoch, though the extreme energies of inflation make direct testing challenging. Another captivating avenue involves exploring the aftermath of inflation during reheating, when the inflaton's energy is converted into familiar particles. Understanding the detailed physics of reheating is essential because it influences the universe's thermal history, the abundance of matter and radiation, and conditions for subsequent processes like baryogenesis, the creation of the observed matter-antimatter asymmetry. Some models connect specific decay channels of the inflaton to particle physics processes that can be investigated indirectly through collider data or astrophysical observations. Reheating also impacts dark matter research. Since dark matter constitutes a large fraction of the universe's mass, investigations into how dark matter particles were produced and how they interact with ordinary matter intersect with inflationary and reheating scenarios. Certain dark matter candidates, such as weakly interacting massive particles, WIMPs, or axions, could have origins linked to processes occurring during or shortly after reheating. Thus, cosmology and particle physics join forces to unravel these mysteries. The energy scale of inflation is another critical aspect that researchers continue to refine. Theories generally place inflation at energies far beyond the reach of current accelerators, around 10-16 billion electronvolts or higher, many orders of magnitude above the energies encountered in particle colliders like the Large Hadron Collider. This scale relates directly to the strength and characteristics of the primordial gravitational waves inflation would produce. If primordial gravitational waves are detected, scientists can estimate the exact energy scale of inflation, a result with profound implications for fundamental physics. It would reveal properties of the inflaton potential and narrow down the space of viable inflation models. Conversely, tighter upper limits on gravitational wave amplitudes constrain inflation scenarios, helping to rule out theories incompatible with observations. The elegance and explanatory success of cosmic inflation raise a natural question. Are there alternative theories that can address the same cosmological puzzles? Over the years, physicists have proposed other models to explain the universe's uniformity, flatness, and structure without invoking inflation. These include bouncing cosmologies, cyclic models, or attempts to modify fundamental physics at high energies. While many of these competing ideas offer interesting perspectives and sometimes resolve specific problems, none match inflation's comprehensive agreement with observational data. Inflation remains the best supported explanation for the earliest moments of cosmic history, though research continues into possible extensions or alternatives in case future evidence points elsewhere. From a philosophical perspective, cosmic inflation forces us to reconsider our notions of uniqueness and fine-tuning in the universe. The smooth conditions created by inflation, followed by quantum-generated fluctuations, suggest that the universe's large-scale properties are not mere coincidences, but emerge naturally from physical laws. At the same time, if inflation is eternal and produces many universes with varying properties, it challenges whether our universe's particular characteristics are special or typical among a vast ensemble. In the end, cosmic inflation serves as a remarkable example of how human insight, grounded in rigorous theory and observation, can peel back layers from the cosmic dawn. It connects the smallest quantum scales with the largest cosmic visible structures, bridging disciplines and challenges. Although much remains to be learned about the precise mechanism and broader implications of inflation, the theory continues to guide contemporary research into the origin, structure, and evolution of the universe. Through the combined efforts of cosmologists, particle physicists, astronomers, and philosophers, the inflationary paradigm stands as a beacon, illuminating the path from our universe's mysterious beginnings toward deeper understanding. One of the most powerful tools that cosmologists employ to deepen our understanding of inflation is the study of large-scale structure. The distribution of galaxies, clusters of galaxies, and the cosmic web itself. These vast arrangements of matter offer a direct window into the primordial density fluctuations seeded during inflation, now magnified by billions of years of gravitational attraction. By carefully mapping how matter clumps and spreads across the universe, researchers can test whether the patterns observed match those predicted by inflationary models. Large-scale surveys such as the Sloan Digital Sky Survey, SDSS, and more recently, the Dark Energy Spectroscopic Instrument, DESI, have collected detailed three-dimensional maps of millions of galaxies, providing an unprecedented look at the cosmic web. These maps reveal intricate filaments and voids where matter is concentrated or sparse. Importantly, the statistical features of these structures, like the clustering strength at different scales, encode rich information about the initial conditions set at the end of inflation. This connection emerges because inflation predicts a near-scale invariant spectrum of primordial fluctuations. The strength of variations in matter density should be roughly the same across a wide range of sizes, with slight variations that depend on scale in subtle but measurable ways. Comparing observed galaxy clustering to theoretical predictions allows scientists to place constraints on the energy scale of inflation and refine models of the inflated field's potential energy landscape. Furthermore, the large-scale structure does not only reflect the initial conditions, but also the cosmic composition, including dark matter and dark energy. Inflation sets the stage for how these components influence the universe's growth over time. Understanding the interplay among initial fluctuations, matter content, and the accelerating expansion driven by dark energy offers a coherent narrative linking inflation to the universe's evolution after its fiery start. Complementing galaxy surveys are cosmic shear measurements, observations of weak gravitational lensing caused by the bending of light as it travels through the universe. As light from distant galaxies passes near massive structures, its path is subtly distorted, a phenomenon that can be analyzed statistically to reconstruct the matter distribution, including dark matter, which does not emit or absorb light. By integrating these measurements with galaxy clustering data, cosmologists achieve a more complete picture of how matter congregated, offering additional tests for inflationary predictions. Moving deeper into the cosmos, the study of primordial gravitational waves remains one of the most tantalizing quests. As highlighted before, these gravitational waves would have been generated by quantum fluctuations in spacetime during inflation, stretching and squeezing the fabric of the universe itself. While notoriously difficult to detect, Their potential discovery would provide a spectacular confirmation of inflation and yield direct information about the physics at energy scales unreachable by terrestrial experiments. The signature of these primordial waves is encoded in the polarization of the cosmic microwave background radiation. Scientists search specifically for a pattern known as B-mode polarization, a swirling form distinct from other polarization types. Detecting B-modes would reveal the presence of gravitational waves from inflation and provide a cosmic fingerprint of the universe's earliest moments. Experiments like BICEP and the Keck Array have pioneered this search, with upcoming projects such as the Simons Observatory and the Lightbird satellite planned to improve sensitivity by orders of magnitude. The challenge lies not only in detecting exceedingly faint signals, but also in distinguishing them from other sources of polarization, such as galactic dust and synchrotron emission. Resolving these foregrounds demands meticulous observational technique combined with sophisticated data analysis. If primordial gravitational waves are observed, cosmologists will be able to gauge the energy scale at which inflation occurred with unprecedented precision. This measurement would influence theoretical physics profoundly, potentially opening new directions in understanding high-energy physics, including candidates for the inflaton and hints of physics beyond the standard model. Besides gravitational waves, the polarization of the CMB encodes other subtle signals reflecting the initial fluctuations. For example, non-Gaussianities, deviations from the simple bell curve statistics expected from standard inflation, could reveal complex interactions within the inflaton field or the presence of multiple fields driving inflationary expansion. Detecting such nuances would help pinpoint which inflationary models best describe reality. Reheating, the phase marking the end of inflation and the transition to the hot Big Bang era, remains another area ripe for exploration. While conceptually understood as the process where the inflaton's energy converts to ordinary particles and radiation, the exact dynamics depend heavily on the inflaton's interaction properties. These details influence how quickly the universe heats up and the relative abundances of particle species formed. Crucially, reheating ties directly to questions about the nature of dark matter and the matter-antimatter imbalance. Certain dark matter candidates could have been generated during reheating, especially if the inflaton decayed into beyond standard model particles. Similarly, processes that create more matter than antimatter, known as baryogenesis, might be linked to the reheating phase, requiring violations of fundamental symmetries and out-of-equilibrium conditions present during that time. Research in this area combines cosmological models with particle physics, aiming to identify testable predictions that can be confronted with astrophysical observations and laboratory experiments. Advances in detector sensitivity for dark matter searches and large particle colliders may help shed light on these connections. The interface between inflation and high-energy physics also opens avenues to explore inflationary scenarios within frameworks such as supersymmetry and string theory. These theories propose extensions to the standard model of particle physics, introducing new fields, symmetries, and dimensions that could underpin the inflaton field's properties. For instance, in string theory, the inflaton might emerge from the dynamics of extra-dimensional geometries or brane interactions. While these ideas remain speculative and technically complex, they illustrate how inflation bridges cosmology with fundamental physics, potentially offering a window into the ultimate theory unifying all forces and particles. The concept of eternal inflation, briefly mentioned before, presents a provocative extension of the standard inflationary picture. In eternal inflation, the rapid exponential expansion continues indefinitely in some regions of the cosmic landscape, spawning countless bubble universes, each possibly featuring different physical constants or laws of physics. This multiverse idea arises naturally from certain inflationary potentials, allowing quantum fluctuations, to occasionally trigger new inflationary pockets. While the multiverse hypothesis pushes the boundaries of empirical science due to its speculative and potentially untestable nature, it influences philosophical discussions about the uniqueness of our universe and the anthropic principle. The idea that some observed properties may be understood as compatible with the existence of observers like ourselves rather than fundamental physical necessity. Whether or not the multiverse exists, the concept demonstrates how inflationary theory leads scientists to profound questions about the nature of reality, the scope of scientific inquiry, and how cosmology may interface with metaphysics. Returning to observable realms, the cosmic microwave background remains a rich source of information. Beyond temperature fluctuations and polarization, it also contains signatures from secondary effects, such as gravitational lensing by large-scale structure and the Sunyaev-Zeldovich effect, the scattering of CMB photons by hot electrons within galaxy clusters. These phenomena provide complementary views of the universe's mass distribution and thermal history, allowing tighter constraints on cosmological parameters shaped by inflation. The connection between cosmic inflation and dark energy, the mysterious component driving the universe's current accelerated expansion, is another intriguing frontier. Both phenomena involve energy intrinsic to space and affect the expansion rate, albeit on vastly different scales and epochs. While inflation operated at extremely high energies ending within microseconds of the Big Bang, dark energy acts at low energy densities billions of years later. Studying inflation's vacuum-like energy and its decay into conventional matter may offer insights into why dark energy became dominant so long after inflation ended and into the universe's long-term fate. Exploring these connections involves both observational cosmology and theoretical physics, seeking a unified picture of spacetime dynamics. In the broader scientific landscape, cosmic inflation exemplifies the synergy and feedback between theory and observation. Precise measurements of the cosmic microwave background, galaxy distributions, and gravitational waves both test inflationary ideas and prompt refinements in models. As technology advances, instruments grow more sensitive, and data sets expand. This cycle accelerates our understanding of the early universe. Moreover, the study of cosmic inflation highlights the multidisciplinary nature of modern research, drawing upon particle physics, astrophysics, general relativity, and quantum field theory. It showcases how progress emerges from integrating diverse perspectives to tackle questions about the universe's origin, composition, and fundamental laws. Public interest in cosmic inflation also reflects the deep human fascination with beginnings, the desire to comprehend how everything started, the physical processes that set the cosmic stage, and our place within this grand narrative. Communicating these ideas in accessible ways fosters broader scientific literacy and inspires new generations of researchers. Looking forward, the next decades promise exciting developments. Experiments aiming to detect primordial gravitational waves will push sensitivity boundaries. Galaxy surveys and lensing measurements will improve mapping of cosmic structure. Particle physics experiments seek evidence of new fundamental particles or forces that might relate to the inflaton or inflationary dynamics. Together, these efforts will clarify inflation's detailed workings and test its robustness against alternative theories. Should unexpected discrepancies arise, they could herald new physics and illuminate pathways beyond the current paradigm. In summary, cosmic inflation remains a cornerstone concept in cosmology, providing the framework to understand why the universe is so large, smooth, and structured in the way we observe. By connecting quantum fluctuations with cosmic evolution, it reveals deep unity in natural laws. While questions about the precise mechanisms and underlying physics persist, Inflation continues to guide the quest to comprehend the cosmos's earliest moments and its enduring mysteries. As research progresses, one particularly promising approach to unraveling more about cosmic inflation involves high-precision measurements of the cosmic microwave background, CMB, radiation's polarization patterns. Beyond just the variations in temperature, the CMB is also polarized, meaning the light waves have preferred vibration directions, a subtle feature imprinted during the universe's infancy. This polarization holds a wealth of information about the early universe, especially about the gravitational waves predicted to have originated during inflation. These primordial gravitational waves would have created a unique, swirling signal in the CMB polarization known as B-mode polarization. Unlike the more common E-mode polarization, which arises from density fluctuations and is symmetrical, B-mode polarization exhibits a curl-like pattern due to the distortion of spacetime itself. Detecting this specific signal would provide strong, direct evidence that inflation did occur and would offer insight into the energy scale governing inflation. Current and upcoming experiments, such as the Simons Observatory, CMBS-4, and space missions like LightBird, are designed with the exquisite sensitivity required to hunt for these faint patterns. The challenge is immense because these signals are incredibly subtle and easily confused by foreground emissions from dust and other galactic sources. Separating the primordial B-modes from these contaminants requires precise instruments, advanced data analysis techniques, and collaboration between multiple observatories. Why is detecting primordial gravitational waves so important? Not only would it affirm inflation's predictions, but the strength of these waves would reveal the exact energy level at which inflation happened. This energy scale could be tremendously high, possibly near the grand unified theory scale, where the electromagnetic, weak, and strong nuclear forces are thought to merge. Knowing this scale would open a window onto physics far beyond current laboratory capabilities, guiding researchers toward a more complete understanding of fundamental forces. In addition to polarization studies, large-scale galaxy surveys provide another vital avenue to test inflationary theory. By mapping the three-dimensional positions of millions of galaxies across vast cosmic volumes, surveys like the Dark Energy Spectroscopic Instrument (DESI) and the Vera-C, Rubin Observatory's Legacy Survey of Space and Time (LSSD) measure how matter clusters and forms structures in the universe over time. These patterns trace the initial density fluctuations seeded by inflation, allowing cosmologists to connect present observations with conditions from nearly 14 billion years ago. These surveys also reveal how dark matter and dark energy influence cosmic evolution. Dark matter acts as the scaffolding on which galaxies build, while dark energy drives the universe's accelerated expansion today. Since inflation seeded the primordial fluctuations from which these structures grow, understanding the detailed distribution of matter offers indirect clues about inflation's characteristics and helps refine cosmological parameters. Another key frontier involves studying primordial non-Gaussianities, subtle statistical deviations from the simple, bell-shaped distribution of primordial fluctuations predicted by standard inflation. Detecting these non-Gaussian signals would indicate complex interactions in the inflaton field or the involvement of multiple fields during inflation. Such discoveries would narrow down viable inflationary models, providing deeper insights into the dynamics of the early universe. Furthermore, the reheating period following inflation continues to be an active focus. Researchers aim to understand the microscopic physics by which the inflaton field's energy converted into ordinary particles and radiation. This phase impacts the temperature and composition of the universe entering the hot Big Bang epoch, and influences the formation of matter-antimatter asymmetry as well as the abundance of dark matter. In particular, certain dark matter candidates might have been produced during reheating, linking the physics of inflation with particle astrophysics. For example, weakly interacting massive particles, WIMPs, and axions, two leading dark matter candidates, could owe their origins to processes connected to the inflaton's decay or to phase transitions immediately after inflation. This interplay between cosmology and particle physics motivates efforts to detect dark matter particles directly or indirectly through astrophysical observations. On the theoretical front, physicists continue to seek a more fundamental understanding of the inflaton field itself. While the inflaton is often treated phenomenologically as a scalar field governing inflation's dynamics, its origin within known or hypothesized particle physics remains uncertain. Some models propose connections with supersymmetry, a proposed symmetry extending the standard model that predicts new particles and potentially stabilizes the inflaton's properties. Others explore frameworks like string theory, where additional spatial dimensions or brane dynamics might naturally give rise to inflationary fields. String theory in particular offers intriguing, if speculative, ways to embed inflation into a comprehensive theory unifying all forces. In these pictures, the inflaton could correspond to geometric configurations or the relative positions of multidimensional branes, whose interactions generate the inflaton potential. Although mathematically complex and challenging to test, such models illustrate how inflation lies at the intersection of cosmology and high-energy theoretical physics. One fascinating consequence of certain inflationary scenarios is the idea of eternal inflation, a process where inflationary expansion never completely ends but continues indefinitely in some regions of space. In this framework, different pocket universes, or bubble universes, continually form by localized ending of inflation, each potentially possessing distinct physical constants or laws. This conceptual multiverse arises naturally from quantum fluctuations influencing the inflaton field and its potential. While compelling philosophically, eternal inflation challenges the boundaries of testable science. Direct evidence of these other universes remains elusive, leading to ongoing debate on how to interpret such models and their role in cosmology. Nonetheless, eternal inflation provides a profound perspective. The universe we inhabit might be only one of myriad domains born from inflation's stochastic and dynamic nature. Returning to observable phenomena, secondary effects in the cosmic microwave background provide further constraints on inflationary theory. For example, gravitational lensing of the CMB by intervening large-scale structures subtly distorts the primordial patterns, allowing scientists to reconstruct the distribution of matter across cosmic time. Similarly, the Sunyaev-Zeldovich effect, scattering of CMB photons by hot electrons in galaxy clusters, offers insights into the thermal history of the universe. These effects complement polarization and temperature measurements, helping to refine cosmological parameters linked to inflation. Another intriguing connection is the relation between cosmic inflation and dark energy, the mysterious force driving today's accelerated expansion. While distinct in scale and timing, both phenomena involve energy intrinsic to space itself. Investigating the vacuum energy responsible for inflation might shed light on why dark energy's effects become dominant billions of years later, potentially revealing deeper connections in the physics of spacetime. High-precision measurements and theoretical developments continue to push our understanding forward. As new observational technologies come online, from next-generation CMB experiments to large and deep galaxy surveys, scientists are poised to test the inflationary paradigm with unprecedented rigor. Simultaneously, particle physics experiments and theoretical models strive to pin down the fundamental nature of the inflaton and its interaction with matter and radiation. In this interplay between the very small quantum fields and fundamental particles, and the very large cosmic expansion and galactic structures, inflation sits at the core. Its study exemplifies how physics across scales intertwines to explain the universe's origin, evolution, and ultimate fate. By continuing to develop experiments aimed at detecting primordial gravitational waves, mapping cosmic structure, and probing the particle physics of reheating, the scientific community hopes to either confirm inflation's predictions or uncover new phenomena that point beyond it. Success in these endeavors would revolutionize our view of the cosmos and the laws governing it. In summary, cosmic inflation is not just a historical event marking the universe's earliest fraction of a second, but a vibrant and evolving field of research. It links the behavior of quantum fields with the cosmic structures around us, frames our understanding of fundamental parameters, and challenges us to expand the horizons of both theoretical and experimental physics. Through this lens, exploring inflation deepens our grasp of nature's unity, revealing the profound interplay of the universe's smallest bits of energy with its grandest scales of space and time. Another essential line of inquiry in inflationary cosmology focuses on the origin and shape of the inflaton potential, the mathematical representation describing how the inflaton field's energy changes over time and space. This potential governs not only the duration and dynamics of inflation, but also the detailed pattern of fluctuations imprinted on the universe. Different forms of this potential lead to different predictions about observable quantities, such as the amplitude and scale dependence of the cosmic microwave background's temperature anisotropies. Physicists explore a variety of potential shapes, often categorized by their complexity and physical motivation. Some models assume simple monomial potentials, like quadratic or quartic functions, while others consider more intricate forms influenced by high-energy physics, such as plateau-like potentials or hilltop scenarios. These shapes affect how the inflaton rolls down the potential hill, with the rate of change influencing the expansion speed and fluctuation characteristics. Testing these potential shapes is a key focus of current and future cosmological observations. For example, the precise measurement of the scalar spectral index, the way fluctuations vary with scale, helps discriminate among models. Certain potentials predict slight deviations from perfect scale invariance, which telescopes like Planck have started measuring with high accuracy. Constraints on the tensor-to-scalar ratio, representing the strength of primordial gravitational waves relative to density fluctuations, also narrow the landscape of acceptable potentials. Beyond the functional form, the concept of slow-roll inflation is central to understanding how inflation sustains itself long enough to solve cosmological puzzles. Slow-roll refers to a regime in which the inflaton field changes gradually over its potential, maintaining a nearly constant vacuum energy density that fuels rapid expansion. Deviations from slow-roll conditions can end inflation or produce distinctive signatures in the primordial fluctuations. Mathematically, slow-roll conditions involve parameters that characterize the steepness and curvature of the potential. If these parameters remain sufficiently small, inflation proceeds smoothly. If they become large, the field loses its hold on the vacuum energy, inflation halts, and reheating begins. Precision cosmology aims to measure observables sensitive to these parameters, tightening the links between theory and measurement. Related to the shape of the inflaton potential is the question of whether inflation is driven by a single field or multiple fields. The simplest and most studied models involve a single scalar field, but multi-field inflationary models are well motivated theoretically and can produce richer phenomenologies, including non-Gaussianities or isocurvature perturbations, fluctuations that affect matter and radiation differently. Multi-field inflation opens an avenue for more complex dynamics, with interactions between fields potentially influencing the duration of inflation and the spectrum of fluctuations. Such models might offer explanations for anomalies observed in the cosmic microwave background, or suggest new observational signatures to pursue in future experiments. Looking beyond classical fields, some inflationary scenarios incorporate effects from quantum gravity or string theory, hoping to embed inflation into a more fundamental framework. String theory, for example, introduces numerous scalar fields known as moduli that could act as inflatons. The landscape of these fields' potentials can be complex, with many local minima, leading to interesting possibilities for the initial conditions of inflation and the likelihood of eternal inflation or multiverse scenarios. This connection to string theory and higher dimensional physics provides motivation to search for specific patterns in the CMB or large-scale structure that could hint at such exotic origins. Although direct detection of these effects remains out of reach for now, progress in theoretical modeling sharpens predictions and guides observational strategies. Another area that touches the physics of inflation is the notion of preheating, a stage immediately following the end of inflation distinct from the more gradual reheating process. During preheating, the inflaton's energy can be transferred explosively and non-perturbatively to other fields through processes like parametric resonance, leading to rapid particle production and possibly the generation of high-energy phenomena such as cosmic strings or other topological defects. Preheating can have important effects on the thermalization of the universe and the distribution of energy among particle species. Its dynamics are highly nonlinear and often require sophisticated numerical simulations to model accurately. Furthermore, preheating could produce gravitational waves distinct from those generated by inflation itself, offering an additional observable channel. Gravitational waves generated during preheating might lie within frequency ranges accessible to future detectors, making them an exciting target for experimental cosmology. Detection would not only confirm aspects of inflationary reheating, but also provide novel windows into physics at extraordinarily high energy scales. Moreover, preheating can influence the abundance of relic particles, possibly affecting dark matter production or altering baryogenesis conditions. These connections illustrate how the inflationary phase's end ties deeply into broader cosmological puzzles. Speaking of baryogenesis, the creation of matter-antimatter asymmetry is still a profound mystery, and inflationary cosmology provides a backdrop against which theorists formulate models of how this asymmetry arose. Since the universe is predominantly matter rather than antimatter, processes violating certain symmetries must have occurred in the early universe. Some baryogenesis models rely on out-of-equilibrium conditions generated during or just after reheating, where decay of heavy particles or phase transitions break charge parity, CP symmetry, favoring matter production. The details of inflation and reheating thus frame the initial conditions for baryogenesis mechanisms. Studying potential links between inflaton decay channels and baryogenesis couplings forms a rich intersection of cosmology and particle physics, offering a path to tie together early universe dynamics with the observed matter content. Returning to observation, the distributions of galaxies and cosmic structures do more than confirm inflation's broad picture. They help test its subtle predictions. Inflationary models predict not only the amplitude and scale dependence of primordial fluctuations, but also statistical properties such as isotropy and Gaussianity. Violations of these properties, for example, anisotropies indicating directional preferences or detectable non-Gaussianities, could hint at new physics during inflation. Cosmologists analyze data sets from galaxy surveys, lensing measurements, and the cosmic microwave background to search for such signals. Advances in analysis techniques, including machine learning and sophisticated statistical tools, enable scrutiny of vast data sets, allowing identification of even tiny anomalies. These efforts could reveal unexpected properties of the inflationary epoch, potentially distinguishing between competing theoretical models. Another exciting development involves the synergy between observations of the cosmic microwave background and large-scale structure. Combining information from both maps provides a more complete picture of cosmic evolution and enhances sensitivity to subtle inflationary signatures. For example, measurements of baryon acoustic oscillations, BAO, patterns in the distribution of matter reflecting sound waves in the early universe, offer precise, standard rulers to map cosmic distances. BAO data contribute to constraining parameters tied to inflation and dark energy, complementing CMB data. Likewise, weak lensing surveys measure the distortion of light from distant galaxies by intervening matter, providing three-dimensional maps of dark matter distribution. This offers additional tests of how initial fluctuations evolve under gravity, linked to inflation's seed perturbations. The integration of diverse observational probes exemplifies how modern cosmology employs multi-messenger approaches, leveraging complementary data to build rigorous tests of theoretical models. On the theoretical front, efforts to reconcile inflation with quantum gravity remain a major challenge. Inflation sits at the interface where quantum effects influence spacetime dynamics on cosmic scales. Reconciling general relativity and quantum mechanics into a consistent framework might ultimately require modifications or extensions to our understanding of inflation. Approaches such as loop quantum cosmology propose that quantum gravity corrections could alter the behavior of the inflaton near the Planck scale, potentially removing the initial singularity or changing the onset of inflation. These modifications might leave subtle imprints on observables, offering empirical handles on quantum gravitational effects. Similarly, string theory-based models explore string gas cosmology or brane inflation, envisioning scenarios where inflation emerges from the dynamics of extended objects in higher dimensions. While mathematically intricate, these theories anticipate novel phenomenology, such as additional particle species or modified gravitational wave spectra. Another development examines the possibility of warm inflation, where the inflaton interacts thermally with radiation during inflation, potentially altering expansion dynamics and fluctuation generation compared to the standard cold inflation scenario. Warm inflation could relax constraints on the inflaton potential and reconcile some tensions with observations. Each of these theoretical variations enriches the landscape of inflationary models, emphasizing the active interplay between fundamental physics aspirations and cosmological data. As the theoretical panorama widens, it also highlights the importance of improving observational capabilities. Planned experiments such as the CMB Stage IV, CMB-S4 project and the next generation of gravitational wave detectors, including space-based observatories like the Laser Interferometer Space Antenna, LISA, aim to push sensitivities to unprecedented levels. These instruments will seek the faint imprints of primordial gravitational waves and other inflationary signatures, providing decisive tests of inflation models, probing physics at energy scales inaccessible to Earth-bound accelerators. In parallel, surveys like the Euclid mission and the Vera C. Rubin Observatory will map billions of galaxies, refining measurements of large-scale structure and offering deeper insights into how initial fluctuations seeded cosmic structures. Together with laboratory experiments pursuing dark matter and particle physics anomalies, this multi-pronged approach strives to unlock the secrets of the inflationary universe. In conclusion, cosmic inflation represents a profound and far-reaching framework that connects the smallest quantum processes with the grand tapestry of the cosmos. Through the study of the inflaton potential, multi-field dynamics, reheating and preheating phases, and the quest for primordial gravitational waves, scientists steadily advance our understanding of the universe's origin. This pursuit exemplifies the unity and creativity of science, blending theory, observation, and technology to illuminate the earliest instance and forge a coherent narrative of cosmic history. While challenges and mysteries remain, the inflationary paradigm continues to provide a powerful lens through which to decode the universe's first moments and the origins of the structure we observe today. An important next step in deepening our understanding of cosmic inflation is to examine how this theory integrates with the concept of quantum fluctuations, not just in the inflated field itself, but in the very fabric of spacetime. During inflation, the quantum properties of all fields, including gravitational fields, are affected dramatically. This leads to the generation of tiny ripples in spacetime known as primordial gravitational waves, which fill the universe with a faint background of gravitational radiation stretching across all directions. These primordial gravitational waves carry special importance since they are distinct from other astrophysical sources of gravitational waves, like merging black holes or neutron stars detected by observatories such as LIGO or Virgo. Because inflation occurred at energy scales enormously higher than anything produced by astrophysical events, the primordial gravitational waves it produced encode information about physics at these extreme energies. Detecting these signals would therefore offer a direct glimpse into the earliest moments of the cosmos and the high-energy processes that shaped its expansion. The search for these primordial waves is ongoing and challenging. They leave their mark most clearly in the polarization of the cosmic microwave background, CMB, radiation, specifically within the B-mode polarization pattern. This subtle curling pattern in the orientation of CMB photons is considered the smoking gun signature of inflationary gravitational waves. Instruments like the BICEP/Keck array, the Simons Observatory, and future missions such as LIGHTBIRD and CMB-S4 are designed to sift through foreground noise and isolate these primordial signals. Importantly, the amplitude of these gravitational waves is quantified relative to the strength of density fluctuations via a parameter called the tensor-to-scalar ratio, often denoted R. Different inflation models predict different values of R, with higher values implying stronger gravitational wave signals. Upper limits on R from current observations already constrain many inflationary models, enabling physicists to exclude certain potential shapes for the inflated field. Discovering a definitive, non-zero R would not only confirm inflation, but also pinpoint the energy scale at which it occurred, helping to direct theoretical physics toward the underlying physics of the inflaton. Another frontier tied closely to inflation is the study of non-Gaussianity in primordial fluctuations. While the simplest inflation scenarios predict that these fluctuations follow a nearly Gaussian distribution, an ordinary bell curve describing random variations, more complex inflationary dynamics involving multiple fields or non-trivial interactions could produce subtle non-Gaussian features. Detecting these deviations in the CMB or large-scale galaxy distributions could discriminate among competing models and shed light on the detailed physics during inflation. These non-Gaussianities are measured through higher-order statistical correlations of fluctuations. Advanced data from Planck and forthcoming missions offer sensitivity capable of revealing such signatures if they exist. The stakes are high because non-Gaussianities could point to more intricate field dynamics during inflation, enrich our understanding of particle physics at high energies, or suggest the presence of additional fields alongside the inflaton. While linking these theoretical predictions to observations is a demanding task, it exemplifies the precision cosmology era we live in. Beyond just measuring broad properties like the overall flatness or uniformity of the universe, scientists now probe intricate statistical patterns, echoes of microphysical processes billions of years ago. Moving from the realm of quantum-induced fluctuations to the transition phase following inflation, the process of reheating remains a key subject. After the rapid expansion phase ends, the inflatoned field's energy converts into a hot, dense mixture of particles. The details of reheating, the timing, efficiency, and particle content produced, directly influence subsequent cosmic evolution, including nucleosynthesis, formation of the cosmic microwave background, and even the genesis of dark matter. Various reheating scenarios have been proposed, ranging from instantaneous decays to more drawn-out processes involving intermediate stages such as preheating. During preheating, nonlinear effects can cause explosive particle production through resonance phenomena, creating potentially observable consequences like primordial gravitational waves, different from those generated during inflation itself. Understanding reheating connects cosmology with particle physics experiments, as the inflaton's decay channels and associated fields may overlap with hypothetical particles studied in laboratories. Moreover, processes during reheating could facilitate baryogenesis, the generation of the observed matter-antimatter asymmetry, through mechanisms that violate symmetries like charge and parity, alongside providing environments out of equilibrium, essential for such asymmetry to develop. In particular, some models propose that right after inflation, heavy particles associated with grand unified theories or supersymmetric partners decay asymmetrically, favoring matter over antimatter. Investigating these scenarios involves combining cosmological observations with collider data and theoretical studies of symmetry breaking, highlighting the interdisciplinary nature of modern cosmology. Alongside these dynamics, reheating sets the stage for the formation of dark matter. Certain dark matter candidates, such as weakly interacting massive particles, WIMPs, or axion-like particles, might have been generated or influenced by reheating processes. Understanding how and when dark matter achieved its present-day abundance is crucial both for cosmology and for designing direct or indirect detection strategies. Expanding focus even further, some recent theoretical models contemplate scenarios where the inflatoned field interacts thermally with other fields during inflation itself, in contrast to the traditional cold inflation picture where such effects are negligible. This concept, known as warm inflation, offers alternative dynamics that could modify predictions for the primordial fluctuations and alleviate some theoretical tensions encountered by cold inflation models. Warm inflation could potentially leave distinct observational signatures in both the amplitude and statistical properties of the density perturbations, thus being testable with refined cosmological data. It also might make certain inflatoned potentials viable that are otherwise disfavored, adding richness to the inflationary model landscape. Beyond technical details, the exploration of inflation continues to prompt fundamental questions about the nature of spacetime and the initial conditions driving the cosmos. For example, why did the universe select a particular initial vacuum state for the inflatoned field? How did this field attain the conditions necessary for inflation to begin? These questions touch on profound aspects of quantum cosmology and the application of quantum mechanics to the universe as a whole. Some approaches propose that inflation began spontaneously from a quantum tunneling event or through a prior phase of the universe governed by physics yet to be fully understood. Theories invoking quantum gravity, still in development, aim to describe these earliest epochs and reconcile inflation with the overall quantum structure of spacetime. One fascinating outcome of this research is the notion that inflation may not have a unique starting point, but could be part of an ongoing process called eternal inflation. In this picture, certain regions of space continue inflating indefinitely while others, like our observable universe, exit inflation to form localized bubble universes. Each bubble could have different physical constants or laws, potentially realizing a multiverse. While eternal inflation remains speculative and notoriously difficult to test, it arises naturally from the quantum behavior of the inflatoned field amidst exponential expansion. This concept challenges conventional ideas about causality, initial conditions, and the global structure of the cosmos, motivating both philosophical and scientific investigation. Returning to the observable universe, advances in experimental capabilities also bring renewed promise in constraining or discovering signs of inflation's legacy. For instance, improvements in measuring the cosmic microwave background's temperature and polarization anisotropies will sharpen constraints on the scalar spectral index and tensor-to-scalar ratio, identifying or ruling out specific inflationary potentials. Simultaneously, large-scale structure surveys covering billions of galaxies over large volumes provide complementary and independent tests. They map how the initial fluctuations from inflation evolved under gravitational attraction, revealing the universe's expansion history and the influence of dark matter and dark energy. These surveys include projects like Euclid, the Dark Energy Spectroscopic Instrument (DESI), and the Vera C. Rubin Observatory's Legacy Survey of Space and Time (LSST). Combining datasets from these diverse observatories enables multi-probe analyses, boosting sensitivity and reducing uncertainties, thus refining our understanding of inflation's parameters beyond what individual surveys can achieve. Additionally, ongoing and future gravitational wave observatories, both terrestrial, like upgrades to LIGO and Virgo, and space-based missions like LISA, seek to detect new sources of gravitational radiation. While these are primarily designed for astrophysical events, certain inflation-related signals might lie within their discovery reach. In lab-based particle physics, efforts to discover new particles, symmetries, or forces linked to the inflaton field or reheating process continue, including searches for axions, supersymmetric partners, or other exotic species potentially connected to the early universe. Such discoveries would have profound implications for inflationary cosmology, providing a much-needed link between the cosmos's largest-scale phenomena and microscopic particle behavior. Altogether, cosmic inflation stands as a paradigm that deeply intertwines the universe's origin story with the fundamental laws of physics across all scales. While it has already revolutionized our understanding of the cosmos, ensuring consistency with a wealth of observations, it also invites ongoing investigation and discovery. By advancing observational technologies, refining theoretical models, and integrating insights from particle physics and quantum theory, scientists strive to peel back the layers concealing the universe's earliest moments. Cosmic inflation thus remains both a foundational explanation and a gateway to further mysteries, expanding scientific horizons as we seek to comprehend the origin and evolution of everything around us. Another critical aspect to explore is how cosmic inflation connects to the idea of symmetry breaking in fundamental physics, a process believed to play a pivotal role in shaping the universe's properties and the forces we observe today. In the high-energy environment of the early universe before the end of inflation, the fundamental forces, gravity, electromagnetism, and the nuclear forces, may have been unified under symmetries that did not distinguish between them. As inflation ended and the universe cooled, these symmetries broke, resulting in the distinct forces and particles that later structured matter and interactions. Symmetry breaking is a widespread concept in physics, seen in phenomena ranging from magnetism to the Higgs mechanism, which endows particles with mass. Within inflationary cosmology, the inflaton field itself may be linked to such a symmetry-breaking event. For example, as the inflaton field rolled down its potential, its value might have triggered phase transitions that split unified forces or altered particle properties, shaping the physical laws that govern the universe afterward. This connection between inflation and symmetry breaking offers a fertile arena for theoretical investigation and observational testing. If certain cosmic relics formed during these transitions, such as topological defects like cosmic strings or domain walls, they might leave detectable imprints in the cosmic microwave background or the large-scale distribution of matter. Although searches for such features have so far not identified definitive signals, they continue to guide observational strategies and model refinements. On a related front, the manner in which inflation ends and reheats the universe can influence particle physics phenomena like the production of dark matter. Some theories propose that particles constituting dark matter were generated from decays or interactions stemming from the inflaton field or phase transitions associated with symmetry breaking. For instance, if the inflaton couples to hypothetical dark sector particles during reheating, their abundance and properties would directly depend on the details of inflation's conclusion. This link highlights how cosmic inflation does not simply inform large-scale structure, but also resonates deeply with microscopic questions about the composition and interactions of matter. The cross-disciplinary nature of this research, involving cosmology, particle physics, and astrophysics, exemplifies the rich, interconnected web of inquiry required to piece together the universe's story. Furthermore, the study of cosmic inflation helps clarify why the universe possesses what physicists call the initial conditions conducive to life. A universe too lumpy or too curved would either collapse prematurely or fail to form complex structures like galaxies and stars. Inflation's role in generating a nearly flat, uniform universe with just the right amount of density fluctuations provides the backdrop enabling matter to assemble into environments supportive of chemistry and, eventually, biology. This realization touches on the anthropic principle, which considers how physical laws and constants might appear fine-tuned for life. While inflation explains many initial conditions dynamically, discussions about its implications often intersect with philosophical questions about why the universe's parameters fall within the narrow ranges observed. In this context, inflation's potential role in eternal inflation and the multiverse hypothesis provides a naturalistic framework. Many universes might exist with varying properties, and we find ourselves in one where conditions favor life simply because only such regions support observers. While the philosophical dimensions are intriguing, the focus remains squarely on empirical science, using careful observations and controlled experiments to test inflation's predictions. The interplay between experiment and theory continues to sharpen inflationary models, helping discard those incompatible with data and refining the parameters of those that survive. Advancing this endeavor, the deployment of next-generation telescopes and instruments promises to deepen our view of the early universe. For example, the recently launched James Webb Space Telescope, JWST, extends observational reach into the cosmic dawn, permitting study of the very first galaxies and stars. While the JWST does not directly probe inflation, understanding the universe's formative epochs helps constrain models by relating early structure formation to initial conditions set by inflation. Similarly, ambitious projects like the Square Kilometre Array (SKA) radio telescope will map hydrogen across vast cosmic times, tracking the universe's evolution with unprecedented detail. By connecting these observations with models of inflationary seed fluctuations, scientists can test the consistency and completeness of the inflationary framework. On the theoretical side, ongoing research explores refinements in the nature of the inflaton field itself. While traditionally modeled as a single scalar field, more advanced theories consider composite fields, non-minimal couplings to gravity, or modifications inspired by quantum gravity. These variants may resolve tensions or anomalies in existing data and predict new phenomena to seek observationally. Additionally, investigations into quantum cosmology seek to merge quantum mechanics and general relativity fully, potentially offering a principled derivation of inflation from quantum principles applied to the entire universe. Such approaches aim to describe the universe's birth as a quantum event rather than a classical singularity, with inflation emerging naturally as spacetime evolves from a quantum state. Though technically challenging, these approaches hold promise for answering foundational questions, such as what sets the inflaton's initial conditions or how cosmic time itself might emerge. Progress in this direction often requires sophisticated mathematics, conceptual innovation, and the eventual hope of empirical tests. Another frontier involves studying the relationship between inflation and gravitational wave astronomy. Beyond primordial gravitational waves from inflation's quantum fluctuations, astrophysical processes during reheating or subsequent phase transitions might generate distinctive gravitational wave backgrounds. If detected by next-generation observatories, these signals could provide direct information about physics at energy scales otherwise inaccessible. For instance, phase transitions involving symmetry breaking could produce stochastic gravitational wave backgrounds, offering signatures of the early universe's thermal and structural evolution. The proposed laser interferometer space antenna, LISA, and ground-based detectors like the Einstein telescope or Cosmic Explorer aim to detect such signals, potentially inaugurating a new era of gravitational wave cosmology. Detecting these signals would help piece together the complex narrative from inflation through reheating to the formation of cosmic structures, constructing a coherent timeline woven from gravitational waves, electromagnetic radiation, and the distribution of matter. In summary, cosmic inflation is not merely a brief episode in the universe's infancy, but a profound principle influencing every scale of cosmic history. From setting initial conditions for the observable universe's geometry and structure to informing particle creation, symmetry breaking, and the conditions necessary for life, inflation's legacy is woven through the cosmos. The continued quest to understand inflation engages diverse scientific fields and pushes the limits of both experimental capabilities and theoretical insight. Future discoveries, whether in the form of primordial gravitational waves, refined cosmic microwave background measurements, large-scale structure surveys, or laboratory particle physics experiments, promise to deepen and potentially transform our understanding. Through this ongoing effort, cosmic inflation remains a shining example of how humanity probes the universe's origins, revealing the unity of physical laws stretching from the quantum realm to the cosmic expanse. It challenges us to advance knowledge, to innovate technologically, and to explore concepts that expand the boundaries of what is knowable, reinforcing the central place of science in illuminating our cosmic beginnings.